Now we need a kinematic viscosity, we need gravity. Those are constants that we are moderately confident of. And we need a length scale in both the Froude number and the Reynolds number. Well, in the Reynolds number, we're looking at the viscous friction. The length scale that's usually used for flow in pipes is the inside diameter. So let's calculate our Reynolds number based on diameter. Now for the Froude number, we're trying to match up the gravitational force, the gravitational potential energy, with the velocity that actually results from it. So the length scale that's probably going to make sense is some average height over which the fluid travels and drops to get to the velocity it has down here. So our average height might be something in here. We might take a length scale of this height, which looks like it's about 5 centimeters. So let's try it out. The data that I got, for cold water, it took a time of about 9 seconds. When I tested with hot water, about 8 seconds, a little faster. And when I tested with room temperature canola oil, it took about 10 seconds, a little slower. Cold dish soap took about 43 seconds, so a lot longer. That's this data point up here. Viscosity of about 0.001 and 43 seconds for it to come out of the funnel. When I warmed up the soap, and I'm not sure just exactly how warm I got it, I wound up with a time of about 27 seconds. And the best guesses I could get for viscosity on these, and this is in meters squared per second for kinematic viscosity. Cold water, really good. Got it out of the book. 1 times 10 to the minus 6. Hot water, again, I got it out of the book. It's pretty close, but I wasn't entirely sure about the temperature, so 5 times 10 to the minus 7, about half as much as the cold water. Canola oil I got from the Canola Institute's website, and they gave me a value of 8 times 10 to the minus 5. So 8 versus 1, 10 to the minus 5 versus 10 to the minus 6. Canola oil almost 100 times as viscous as the cold water. For dish soap, all of the estimates I got fell into the range somewhere around 1 times 10 to the minus 3. And they varied quite a bit. If the dish soap was warmer, it might be about half the viscosity. And that's pretty dodgy. Like I said, there's a pretty big error bar on that, and probably a pretty big error bar on this one as well. These ones down here, I'm much more confident about. So if I look at the velocity and calculate it based on my 6.5 divided by t, to get a velocity in meters per second, I get 0.72, so almost 1 meter per second for the cold water, and 0.81, even faster for the hot water. 0.65 for the canola oil, so still fairly high value. And for the cold soap, going much more slowly, 0.15. And the warm soap, 0.24. So they're all in the same range, from 1/4 to 3/4 sort of range. There's a factor of about 3 in there in the velocities. How does that turn out in terms of the Reynolds number? If I calculate my Reynolds number, characteristic velocity times diameter divided by kinematic viscosity, for the cold water I get about 5,040. For the warm water, 11,340. For the canola oil, 57. For the cold soap, 1. Or the warm soap, about 3. So some very different values for Reynolds number. And we usually expect in pipe flow that we'll see a transition from nice orderly laminar flow to not so orderly turbulent flow round about 2300 for a Reynolds number. So we really expect that flow and that flow to be qualitatively different. Now let's look at the Froude number. If we calculate the Froude number based on this height h, so we'll calculate u over square root g and h, where h is about 5 centimeters. The numbers we get are 1.0, 1.2. So this would suggest that the magnitude of the gravity forces and the resulting inertial motion are about the same. Now, because of the idealizations we made here, this is just an approximate comparison, but still it shows that they're about the same order of magnitude. And for the canola, 0.9, so still in the same order of magnitude, gravity versus inertia. Cold soap, 0.2, the warm soap, 0.3. Much lower conversion from gravitational potential energy into inertial kinetic energy of the velocity. So the forces don't match up. The energy has gone somewhere else. It's gone into the highly viscous nature that we see here because of the low Reynolds number. So both the Froude number and the Reynolds number help us see the relative importance of the different forces and tell us a little bit about what's going on. And looking at this now, I can say, okay, up here, the inertial forces aren't really very important. They're not even really very important for that data point. But they're starting to get important for this data point. And they're very important for that data point. And in this region down here, the flow is being dominated by those inertial effects. There's still a small variation due to viscosity, but the inertial effects really dominate down here. This is all about gravity accelerating the fluid to get it out of the funnel. Up here, the viscous effects are dominating. I can see that the Froude number is low, meaning that we've got a low amount of inertial force compared to the gravitational force. So that gravitational force must be opposing something else. It's opposing this much higher level of viscous force as indicated by the Reynolds number. High viscous force, this area dominated by viscosity, this area down here dominated by inertial effects. So we can get a lot of understanding of what's going on in our flow by examining the relative magnitude of the forces without actually doing the much more complicated calculation on exactly how fast the fluid is moving at a given time in a given location.